After a rather long hiatus in between, I am trying to resume my series of lectures on path integrals in quantum mechanics. Since it has been a rather long time since I last talked about this, let me just quickly recapitulate some of the basic things that we had learned about in previous lectures. This will help me recollect what was going on, as well as sort of ensure that there is some degree of continuity in notation between the previous lectures, which are now nearly a year old, and these ones. Let me remind you that the central player in our story was the propagator K xbtb semicolon xata. This basically tells us that if you know that a particle is at xa at time ta, what is the probability amplitude for finding it at the location xb at time tb? Now, this can be written as the overlap between the states xb, tb and xa, ta, where xa, ta stands for the eigenstate of the x operator at time ta with eigenvalue xa. And similarly, xb, tb is the eigenstate for the x operator at time tb with eigenvalue xb. Of course, when we are saying this, we imply that we are using the Heisenberg representation in which the operators are time dependent, so the eigenstates of the operators are themselves time dependent. If you move over to the Schrödinger picture, what you get is that the same expression can be written down as a matrix element between the eigenstates xb and xa of the position operator with eigenvalues xb and xa respectively, or the time evolution operator u, tb, ta, which is the operator which talks about the evolution of states in the Schrödinger picture from time ta to time tb. And if you have a Hamiltonian describing the system which is time independent, u, tb, ta, as you all know, is e to the power minus I h into tb minus ta by h bar. And all that is going to follow, I am going to assume that tb is bigger than ta. Now, as we had also seen before, that if we talk about the special case when the Hamiltonian is of our familiar form, it's p square by twice m plus v of x, where v of x is the potential energy, and p square by 2m is of course a kinetic energy term written in terms of the momentum operator, then the expression for k xbtb semicolon xata can be rewritten in the form of a path integral. This is something we had already seen in our very first lecture in the series. And in this particular case, the expression that we derived turns out to be the following rather complicated looking thing. It's a limit as small n goes to infinity of this factor m by 2 pi I h cross epsilon raised to the power n plus 1 by 2 multiplied by a multiple integral over small n variables dx1, dx2, dxn ranging from minus infinity to plus infinity of this integrand, the exponent of I epsilon by h bar, sum from j running from 0 to n of m by 2 xj plus 1 minus xj by epsilon whole squared minus v at xj. Now, if you look at what is really being done here, what we are doing is the following. We are taking the interval from ta to tb and chopping it up into n plus 1 equal intervals. The endpoints t0 is ta and the other endpoint is tn plus 1. Since you have n plus 1 intervals, you must have n plus 2 points and the points are labeled from 0 to n plus 1 here. Tn plus 1 has to be tb, and that means epsilon, the size of the interval, has to be tb minus ta by n plus 1. And by xj, what I am denoting is the value of x at tj. So we have equally spaced time instants t0, t1, t2, t3, tn, tn plus 1, and at each time instant the location of the particle is denoted by the corresponding x with that index xj is x of tj. So if you look at this, all we are doing is we are allowing the location of the particle at intermediate times to range all over the place from minus infinity to plus infinity. And apart from this rather messy looking overall factor, what we are doing here is the following. xj plus 1 minus xj by epsilon is nothing but the distance which the particle moves in the jth interval from tj to tj plus 1 divided by the width of the interval epsilon. That of course is the speed of the particle in that interval. You're squaring this here, so this is nothing but m by 2 x dot square or kinetic energy minus v of xj, that is the potential at that interval. Of course, we ultimately are going to take the limit where n goes to infinity, each interval shrinks down to a very, very small value. So this essentially is the value of the Lagrangian mx dot square by 2 minus v of x at the jth interval. You are summing up the value of the Lagrangian over each interval after multiplication by an epsilon. That essentially is what you do after you take the limit n goes to infinity, of course, when you want to calculate the integral of L with respect to time from time ta to time tb, which is what we know as the action. So what we are really saying is we will allow all possible paths which start at xa at time ta and end at xb at time tb. And since we are integrating over all possible values of the intermediate x's, we are going to actually allow all possible paths. So what we are doing is something which is called a path integral, and that is symbolically written here by this curly d of x, which is shorthand for this entire thing in the limit n goes to infinity. And what we are integrating is exponential I by h cross times the action for a particular path x. Remember, s, the action, is a functional. It depends on the function x of t. So given a function x of t, we get a corresponding functional. Each path corresponds to a particular value of the action. What you're doing is you're weighting each path by a phase factor e to the power I by h cross times the action and summing up over all paths. This essentially is the path integral formulation, at least for the special case where the Hamiltonian is a kinetic energy p square by 2m plus the potential energy v of x. To carry on with the recapitulations, let us remind ourselves of how we figured out the propagator for the free particle, the special case where v of x is 0. The exponent that we have here, I epsilon by h cross times this sum, simply becomes I epsilon by h cross j goes from 0 to n of m by 2 into xj plus 1 minus xj by epsilon whole square. By taking the m by 2 and epsilon square out of the sum, I end up with this slightly simpler expression. Im by twice h cross epsilon, sum from j equal to 0 to n of xj plus 1 minus xj whole square. At this point, it is important to remind ourselves that the integral that we are going to carry out is over x1, x2, x3 up to xn. So all the x's that you see in this sum are actually not subject to the integration. Most of them are, but x0 and xn plus 1 are actually constants as far as the integration is concerned. Remember, all the paths that we are talking about will start at x0, that is xa, and end at xn plus 1, which is xb. So they are constants, they don't change from path to path. Taking that into account, what we will do is we will split up this sum slightly. Apart from this Im by twice h cross epsilon factor, you have two terms, one coming from the j equal to nth term here, the xn plus 1 whole square, and the other coming from the j equal to 0th term, the x0 square. So these are the two terms that you get, which are independent of the integration variables at all. Then you have terms which are triboidally quadratic in the integration variables. However, there are two terms which are linear in the integration variables. Those are the cross terms, the twice AB kind of terms that you get from the j equal to n and j equal to 0 terms, the two extreme ends. That gives you minus 2 times xn plus 1 xn plus x1 x0. These are of course not constants. Xn and x1 are actually integrated. They do depend on the path. However, these terms are linear in the variables over which you are doing the integration. On the other hand, for all the other j's, that is from j equal to 1 to j equal to n, you have xj square, but it comes twice. Once from xj plus 1 whole square, again from xj square. So you get twice xj square, and it will take a little bit of thought to convince yourselves that the cross terms can be written down as twice xj plus 1 into xj. That's sort of trivial. Because you have already taken the j equal to 0 cross term here and j equal to n cross term here, this term actually goes from j equal to 1 to n minus 1. Now, as we have seen before, you could rewrite this in the form which is known as a quadratic form or an inhomogeneous quadratic form for mathematicians. You have a constant term c. You also have a linear term b transpose x and a quadratic term minus x transpose a times x. And A here is this big matrix. This n by n matrix. This is wrong. This is n by n. And this one is n by 1. A is a square matrix which is tridiagonal, which essentially gives you the 2's down the diagonal. And the minus 2 xj plus 1 xj is taken care of by a minus 1 on each side of the diagonal. So you get a tridiagonal matrix with an overall factor of m by twice h cross epsilon I here. Remember, you had an I in the numerator here, but because of the minus sign, what we have done is we have moved the I from the numerator to the denominator. Now the linear term can also be written down in terms of a product of a column vector x. This x here, of course, stands for the column vector x1 down to xn, all the variables you're going to integrate over. Now, B is a very sparse matrix because notice that in the linear term, only x1 and xn contribute, all the other integration variables x2, x3, etc. do not contribute at all. So, B actually has non-zero components only in the very first one, which will be multiplied by x1 when you form btx, and the last one, the one which will be multiplied by xn. So this is xn plus 1 here. And C, of course, the constant is simply I m by twice h cross epsilon xn plus 1 whole square plus x0 square. This, of course, is nothing but the exponent that you have to integrate over x1, x2, x3 up to xn. For this, we make use of the standard Gaussian integration result, that this integral over x1 to xn, ranging from minus infinity to plus infinity for each one of them, of this exponential of this quadratic form, happens to be pi to the n by 2 by square root of determinant of a e to the power 1/4 b transpose a inverse b plus c. This is the formula which we derived, if I remember correctly, in the second lecture of the series. Or perhaps in the first, I don't really remember exactly right now. But using that, basically our propagator for the free particle works out to be this particular expression, m by 2 pi h cross I epsilon to the power n plus 1 by 2. That's the factor that was there outside. Minus 1/4. Then you will have an exponential c plus 1/4 b transpose a inverse b. That's this term times pi to the n by 2 by root over determinant of a. After this, given the fact that we already have the matrices in hand, capital A and the column matrix B, we can explicitly calculate this thing, and we found out that the final result was square root of m by 2 pi h cross I into tb minus ta times an exponent of I by h cross times the classical action. S classical is nothing but the action calculated along the classical path. So this is the result for the propagator for the free particle. I'm not going to go into the details of the calculation simply because I've already discussed that before. Our main aim in today's lecture is to discuss the propagator for another very simple system, the harmonic oscillator. However, before we go there, let me point out that this calculation for the free particle turned out to be a bit more complicated than we expected. Not only did we have to calculate the determinant of a small n by small n matrix, after all, that's a huge matrix and the limit when n goes to infinity, we also had to calculate its inverse in order to determine the 1/4 B transpose A inverse B term there. Note that this 1/4 B transpose A inverse B term has to be calculated because B is not a zero column vector. There are linear terms in the exponent of the integrand. Of course, you don't really need to calculate all of A inverse. What you need essentially are A inverse 1, 1, A inverse nn, A inverse 1n, and A inverse n1. It would be very nice if we did not really have to calculate A inverse. And there is a nice cool trick which allows you to do that in the case of a free particle, and later on, as we will see, in the case of the harmonic oscillator as well. In order to do this, we will do something which is actually suggested by the final result. Note, we were integrating exponential of I by h cross times the action for a given path over all possible paths with a rather complicated integration measure and so on. But once we did the calculation, we ended up with exponential I by h cross times the classical action, that is the action for the classical path, times an overall factor. Now this actually should suggest the way forward. What if the paths that we considered were considered as fluctuations around the classical path? So we have an x classical of t, which is a solution for the classical path for the free particle in this case. And our x of t for a given path would be x classical of t plus capital X of t. The capital X of t is a deviation from the classical path for this particular path that we are talking about. Now, x classical t is very, very easy to figure out. After all, we are talking about a particle which is free. So in the classical world, this particle would move with constant velocity. And the velocity, of course, would be xb minus xa by tb minus ta. And it will be at, sorry, this is wrong. This will be at xa when t is equal to ta. So what we really need to do is write this as t minus ta. That's the displacement in the time up to time t plus the original position at time ta. So this is your classical x, and your capital X is a deviation from this capital X. But because we are only considering paths which start and end at xb and xa, what we must have is our deviation, capital X, must vanish at ta and tb. Now you should realize that the reason why we love this is that the complicated B transpose A inverse B term came out because we had a linear result, and that came from the two endpoints. If the two endpoints had x's which were 0, the linear term would not have been there, and all you would have to calculate is the determinant of A, not its inverse. So that is the reason why we are looking at a different variable where there is no variation at the ends. We are talking about the classical path, and we are looking at fluctuations about that. Now, what's so special about the classical path? You might very well have started with any given path joining xa, ta and xb, tb, and talked about deviation from that path. And that would, of course, have given you capital X of ta and capital X of tb, both 0. But that is not the only good thing that you get here. And in order to understand that, what we need to do is take a look at the action for this arbitrary path, small x. Of course, our Lagrangian here is just half mx dot square, and that's just what we are integrating from time ta to time tb with respect to time of. Now since x dot is x dot classical plus capital X dot, our action can be written in this form. And using our childhood formula, we can split this up into three pieces. Half m ta to tb x dot classical whole square integrated over time, which of course is nothing but the classical action, or the action for the classical path, to be more precise. We get a cross term here, m integral from ta to tb x dot classical capital X dot with respect to time. And finally, we have a term which looks like our original action, but small x has been replaced by capital X dot here. Now, this term is just the classical action. That will not change when you change your path. The classical path is a fixed path and you are talking about deviations from that. So this is essentially a constant as far as our path integral is concerned. This term essentially looks exactly like our original action, except that we are doing this for a particular variable which vanishes at the two endpoints, thus leading to the advantage of not having to deal with linear terms in the Gaussian integral. But what about the middle term? Now the middle term can be written down in a very familiar form. You can write down x dot cl capital X dot as a derivative of x dot cl times capital X. Of course, that's not right, but that means that you have to take away from this x double dot cl times capital X. So this term and this term together give you this one. Now the reason why I am doing this is the following. This, of course, can be integrated trivially. It becomes small x dot cl capital X at tb minus the value of the same thing at ta. But remember, capital X vanishes at tb and ta, so this term actually goes to 0. Now all that we have said so far would work if we had used any path from xata to xbtb instead of the classical path. However, what the classical path will also ensure is that this term vanishes because the equation of motion that we have along the classical path tells you x double dot cl is actually 0. So these two additional pieces vanish, and so the action for an arbitrary path small x can be written down as a classical action plus a term which looks very much like the classical action, except that instead of small x classical, you have put in capital X here. Let us now return to our original expression for the path integral. Now, in order to calculate the propagator, we had to integrate over small x1, small x2 up to small xn, where these were the values of the position that the particle had along a particular path at equally spaced time intervals. Now, since the x classical 1, x classical 2, x classical 3, etc. are fixed quantities for each one of the time intervals individually. Of course, it changes from interval to interval, but at each time instant, it's a fixed quantity. So, if you moved from small x1, small x2 to capital X1, capital X2, which are nothing but corresponding capital X's at t1, t2, tn, all you're really doing is shifting the integration variable by a constant amount. So that can be done without any other change. So you have this integral from minus infinity to plus infinity of d capital X1 up to d capital Xn times exponent I by h cross of s, which can be split up into exponent of I by h cross s classical times the exponent of this integral, which we can break up into this discrete sum. So finally, what this really becomes is exponential of I by h cross times s classical into a function of tb and ta. The rest of the stuff that you have here, all of this and this, if you just leave this term out, will ultimately depend only on ta and tb, and this is the overall normalization factor that our propagator will have. Now we already know what this normalization factor is because we have explicitly calculated the propagator for the free particle earlier. However, we can pretend that we haven't done anything of that sort. So we can now try to calculate this correction factor or normalization factor by evaluating this integral explicitly. We can of course pretend that we have not done this calculation earlier and figure out this normalization factor f of tb, ta by evaluating these multiple integrals explicitly using our standard Gaussian integration and then taking this limit. And it should not come as a surprise that once you do that, you are going to get the correct overall factor for the propagator for a free particle. But let me just remind you once again that the reason why this calculation is going to be substantially simpler is that there is no linear term to worry about here. You might expect a linear term to come from the two endpoints. At the two endpoints, you are going to get capital Xn plus 1, capital Xn at the upper end and capital X1, capital X0 at the lower end. But because capital Xn plus 1 and capital X0 are both 0, these linear terms would just vanish. So our overall calculation will become much simpler. Now I am not going to repeat the calculation here for the simple reason that we have done a more involved version earlier. But I am going to now show how we can use this notion to calculate the propagator for a harmonic oscillator with relative ease. Now for a harmonic oscillator, our starting point is the Lagrangian, which is m by 2 x dot square minus omega square x square. The integral of this Lagrangian, of course, is the action, which is going to play a stellar role as the thing which is there in the integrand for the path integral. We are going to use fluctuations about the classical path. So x of t is x classical of t plus capital X of t. And x classical of t, as we all know, obeys a standard harmonic oscillator differential equation. X double dot classical plus omega square x classical is 0. And because we are all considering only paths which begin and end at small xa and small xb respectively, as in small x classical already does that for us, at least that's the classical path that we are choosing, capital X at ta and capital X at tb must vanish, which of course means capital X0 and capital Xn plus 1 are both 0. Now let us try to see whether the same simplification that we had seen in the case for the action for the free particle also continues to hold here. If we calculate the action for an arbitrary path small x of t, we have to replace small x by x classical plus capital X. The x dot square becomes x dot classical plus capital X dot whole square. The omega square x square becomes omega square x classical plus capital X whole square. You have to, of course, integrate this thing. But now, we are going to follow the same routine that we had followed earlier for the free particle. By collecting together terms which involve the x classical alone, we get m by 2 x dot classical whole square from here, minus m by 2 omega square x classical square from here. And this, of course, will give us the classical action, or more precisely, the action for the classical path. With the cross terms in the squares, the twice AB terms, I'm going to get two terms which are a mixture, which have both x dot classical and a capital X dot, and x classical and capital X. So that's what you have here. Finally, you have the term which has only capital X and no x classical. That's the square term from this and also the square term from this combined. So which essentially looks exactly like our original s of x, but with x classical replaced by capital X. Now, we have to check whether the cross term here vanishes as it did for the free particle. And to see that, what we need to do is take a look at this term once again, x dot classical capital X dot. We need to integrate that. We change that into total differential of x dot classical times capital X. the reason why we are looking at x dot classical times capital X and not, for example, x classical times capital X dot is that this one integrates to simply x dot classical capital X at the two endpoints, subtracted from each other, of course, but capital X vanishes at the two endpoints, so this term will integrate to 0. Of course, in addition to this, you have to correct for the product formula by putting in this term minus x double dot classical capital X integral from TA to TB with respect to t. But now comes the classical equation of motion. X double dot classical is actually minus omega square times x classical. If you plug that in, this term becomes integral from TA to TB of omega square x classical times capital X dt. And this integral, which can be integrated out using the fundamental theorem of integral calculus, is simply 0, as we have already explained. But note that if you take the other cross term that you had here, this one and this one, they cancel each other out. So once again, the cross terms vanish and you are left with Sx equals S classical plus m by 2 integral from TA to TB of capital X dot square minus omega square capital X square with respect to time. And once again, by going over from the small x variables to the capital X variables, fluctuations from the classical path, our propagator will end up taking this form. E to the power I by h cross S classical. That does not depend on the particular path followed, so that's an overall constant factor which comes out, times this normalization factor f of tb comma ta, which we will get by carrying out the discretized path integral version, but this time, instead of using xj plus 1 minus xj by epsilon whole square, you have to supplement that with a minus omega square capital xj square. So this is what f of tb comma ta will look like. We have to evaluate this limit, and the reason why this limit is easier to evaluate than working directly with the small x's is, as I stressed before, capital X0 and capital Xn plus 1 being 0, this quadratic piece here does not give rise to linear pieces which depend only on one factor of xn or one factor of x1, because the corresponding multiplying factors xn plus 1 or x0 would be 0. So this is very, very similar to the free particle case, except that you have an additional minus omega square epsilon square stuck here. So we can proceed in a very similar fashion. All you have to do is look at this particular integral. There is of course this overall normalization factor m by 2 pi I h cross epsilon to the power n plus 1 by 2. But apart from that, you have this multiple integral over capital X1 to capital Xn of exponential minus xt ax, which we know has to be pi to the n by 2 by root over determinant of capital A. Let me stress once again, no linear terms, so no 1/4 B transpose A inverse B to worry about, no need to calculate the inverse. A here is slightly different, and only slightly different, from the corresponding matrix that we had for the free particle. Apart from this factor of m by twice I h cross epsilon, what you have is a tridiagonal matrix with the leading subdiagonals having only minus ones, as we had in the case of the free particle. The only real difference here is that instead of a 2, which you had down the diagonal in the free particle case, here you have 2 minus omega square epsilon square for each one of the diagonal elements. Other than that, this matrix is very, very similar. And the way in which we can calculate its determinant is also very similar to what we did for the free particle case. Now it's obvious that the determinant of the matrix capital A happens to be determinant of this matrix that you can see here times this constant to the power small n, where small n of course is the size of the matrix. Now dn, as we argued for the free particle case before, we can argue along the same lines to show that dn obeys this particular recursion relation. Dn has to be 2 minus omega square epsilon square dn minus 1 minus dn minus 2. If you have forgotten how that argument went, let me just remind you that it's going to be this element times the corresponding minor, which is dn minus 1. Then you have to take this element and find its corresponding minor. In the corresponding minor, you will have one column which has only minus 1 here. Every element is 0. So you take this element times its corresponding minor, which is going to be the dn minus 2. This is pretty straightforward. We have done this before for the free particle. The same idea works here. Now, this is a recursion relation that we need to solve, but you need initial values for this, and the initial values that are obvious here are, for the 1 by 1 matrix, d1 is simply 2 minus omega square epsilon square, just a single element sitting here. For a 2 by 2 matrix, you have 2 minus omega square epsilon square whole square minus 1. So that's d2. Now we can of course solve the problem using the values of d1 and d2, but it will actually turn out to be easier if we use the recursion relation to push it backwards to find out d0 and d minus 1. Now it's very easy to see. If you put in n equal 2 in this expression, d2 should be 2 minus omega square epsilon square d1 minus d0. And from these values, it's very easy to see that d0 works out to be 1. We can actually push it back further by putting in n equals 1. This will give me d minus 1 according to this formula. And d minus 1 will turn out to be even simpler. It's just 0. Now, in all recurrence relations like this, there is a very simple ansatz which will help us to solve this particular difference equation, which is, let's assume that dn is some constant r raised to the power n. If we plug this here, we will get r to the n minus 2 minus omega square epsilon square r to the n minus 1 plus r to the power n minus 2 equals 0. And by cancelling out the r to the n minus 2 from both sides, we will end up with a quadratic equation. R square minus 2 minus omega square epsilon square r plus 1 equals 0. Let me remind you once again that this is very, very similar to what we had for the free particle case. But in the free particle case, we would have ended up with r square minus 2r plus 1 equals 0. Quadratic equation which would have given us 2 equal roots. So finding out the most general solution from there would require a bit more work. Here things are actually simpler. There are 2 roots which we are going to denote by r plus and r minus, corresponding to the plus minus sign in the square root of b square minus 4ac. But it's also very easy to see that in this case, for this equation, the product of the roots is plus 1. And it's also very easy to see that the roots have to be complex because the discriminant would be negative. So, you will have complex roots whose product is plus 1 and whose sum is 2 minus omega square epsilon square. So, its sum is real. That means the two roots obviously have to be complex conjugates of each other. And we can write them as e to the plus minus I phi. Remember, we are going to be interested in the case where n becomes very, very large, and that means epsilon becomes very, very tiny. Now, in the limit epsilon becomes very, very tiny, this expression, if this were cos phi, we would just have to use our standard result that for small phi, cos phi is like 1 minus phi square by 2 to realize that phi in the limit of very small epsilon would have to become omega epsilon. Of course, there will be higher order correction terms, but for very small epsilon, phi can be replaced by omega epsilon without any problem. In fact, the imaginary part, of course, is plus minus I sin phi, and that also works out rather nicely from phi equals omega epsilon. Now that we have 2 different r satisfying our recursion relation, the general solution will be capital A times r plus to the n plus capital B times r minus to the n. That's dn for us. And using d0 and d minus 1, we end up with these 2 very, very simple relations which will help us calculate the constants a and b. A plus b is 1 and a by r plus b by r minus is 0. This one, of course, is d0 and this is d minus 1. And now it's just a matter of simple algebra, simple high school algebra, to figure out what our A and B are going to be. And very, very simple calculation shows that A is e to the I phi by twice I sin phi, and B is minus e to the minus I phi by twice I sin phi again. And now if we plug these things back in our expression for dn turns out to be this. A times e to the I phi raised to the n, that's e to the I n plus 1 phi by twice I sin phi, and a similar term for B. And this simplifies to sine of n plus 1 phi divided by sine of phi. So this is the expression for dn that we have. This actually becomes even simpler because remember we are only going to worry about the situation where epsilon and hence phi is very, very, very small. By the way, I have just realized that I have been guilty of lousy notation. The A and B constants that we have used here, at least one of them, A, is also the symbol that I use for my matrix A, the n by n coefficient matrix. However, I'm pretty sure that none of you will confuse the n by n tridiagonal matrix with this simple numerical coefficient. In any case, we will not need these A and B constants any longer. So, let's go back to figuring out what the determinant of A is, and from that, what the normalization factor in front of my propagator is. Since dn is sine of n plus 1 phi by sine of phi, let me just remind you that det A is m by twice I h cross epsilon raised to the n times that, and our multiple integral that we wanted to evaluate, the Gaussian integral, is pi to the n by 2 by square root of determinant of A, that is pi to the n by 2 times twice I h cross epsilon by m to the power n by 2 by root over dn. Taking into account the factor that we have from the measure, you ultimately end up with this expression for the normalization factor f of tb comma ta is a limit as n goes to infinity of m by twice pi I h cross epsilon to the power n plus 1 by 2. This is the factor that was there in the normalization all along, multiplied by pi to the n by 2 divided by the square root of the determinant of A. And as you can easily see, there is quite a lot of scope for cancellation here. In fact, you get 2 pi I h cross the by m to the power n by 2 if you take the second and third terms together, and that cancels most of the m by 2 pi I h cross epsilon, leaving you with just one square root factor. Of course, overall what you get is the square root of m sin phi divided by 2 pi I h cross epsilon sine of n plus 1 phi. Note that in the limit that we want to take, as n goes to infinity and epsilon goes to 0, phi essentially becomes omega epsilon and sine of phi can be replaced by omega epsilon. So, if you take that into account, then what happens is you end up with m omega epsilon in the numerator and 2 pi I h cross epsilon sine of omega n plus 1 epsilon in the denominator. Using the fact that n plus 1 epsilon is nothing but the total time interval, that is tb minus ta, this simplifies to the following expression: square root of m omega by 2 pi I h cross sine of omega tb minus ta. So this is my overall normalization factor, and the propagator is simply this factor times exponential of I by h cross times the classical action. So we have figured out the propagator for the harmonic oscillator. All that is left is actually figuring out exactly what S classical is in terms of the initial and final points XATA and XBTB. In order to do that, we fall back on the fact that for the classical path, we have the simple harmonic oscillator solution that is familiar to all of us. X classical a function of t, is given by a cos omega t plus b sin omega t. And its derivative, of course, is simply minus omega a sin omega t plus b omega cos omega t. So the Lagrangian, at least along the classical path, is given by half m x dot classical squared minus omega squared x classical squared. And squaring the two expressions above, multiplying the first one by omega square, subtracting, and collecting terms together using very simple algebra and a bit of trigonometry, what you get is that the Lagrangian becomes half m omega square times b square minus a square multiplied by cosine twice omega t minus twice ab sine twice omega t. Now, it is very easy to find out the classical action. After this, all you have to do is integrate the above expression for Lagrangian with respect to time from Ta to Tb. And that integration is absolutely trivial and gives rise to this expression that you can see right now on your screen. Now, a bit of trigonometry once again using the difference formula, the formula for sin A minus sin B or cos A minus cos B, actually tells you that sine of omega Tb minus Ta is common to both of the factors that you see out there. Of course, what I have done when we go from here to here is I have taken the twice omega factor out. But there was a 2 which comes in from the trigonometric expression, so that's why I only have a m omega by 2 outside. And all I have done here is just use the simple trigonometric sum to product, or rather difference to product rules. And by taking the sine omega Tb minus Ta common, this is the expression we get for the classical action. However, this is still not done because we want to express the classical action in terms of xa, Ta, xb and tb. The capital B and capital A, I am guilty once again of using the same letters for different purposes, but we are done with the n by n square matrix or with the coefficients for dn. So from now on, our A and B are just constants of integration in the solution of the classical differential equation obtained by the harmonic oscillator. Anyway, what we need to do is get rid of the A and B in favor of XA, TA and XB, TB. How do we do that? Pretty straightforward. By putting in the fact that at t equal to Ta, x is XA, and at t equal to TB, x is XB, we get these two equations. And we need to solve them for capital A and capital B. And that's straightforward. All you have to do is take the coefficient matrix cos omega Ta sin omega Ta cos omega Tb sin omega Tb, invert that and hit XB XA with that. Okay, you may be worried about the order XB XA here. I have just reordered the two equations. So a simple job of inverting the matrix, 2 by 2 matrices, as I have already said several times before. It's very easy to invert. All you do is change the sign of the off diagonal terms and flip the diagonal terms and divide by the determinant. The determinant is minus sine of omega Tb minus Ta, which is why here the diagonal terms have flipped and changed sign and the off diagonal terms have stayed the same. So this is what you get for capital A and capital B in terms of XA and XB. A simple solution of the initial value problem. Or rather boundary value problem. XA, Ta, XB, Tb are the two boundaries of the path and A and B are determined from that. Of course, we don't really need A and B. We need the combinations B square minus A square and twice AB. Again, very simple trigonometry, but frankly, it's easier to follow this if you work this out on your own. If you square B and square A and subtract, of course, sine square omega Tb minus Ta is going to come out as an overall factor. But let me just focus on xa square, which you get from b square and a square. B square minus a square is going to have cosine square omega Tb minus sine square omega Tb. That, of course, is cosine 2 omega Tb. Very similarly, xb square can also be seen to have the same or similar coefficient, cosine twice omega Ta. And you can continue and figure out that the coefficient of 2xa xb is cos omega Tb plus Ta. Well, twice AB, you just multiply the two together, throw in an extra 2, And it's pretty easy to see that you are going to get something which looks very similar to the previous one, except that xb has been multiplied by sine instead of cosine again. Now comes the time to put all of these together and try to write down S classical. Well, S classical is basically b square minus a square times cosine of omega tb plus ta minus twice ab times sine of omega tb plus ta. Apart from the factor, common factor which you get outside. Now, if you collect all the terms together, xs squared, xb squared and twice xb separately, once again, this is much easier to follow if you actually work it out yourself. Anyway, once you collect all these terms together, this is what you are going to get. And if you take a look at these two terms as cos A cos B plus sin A sin B, cos of A minus B, which is cos of omega TB minus TA. In fact, the coefficient of xb squared is exactly the same. And the coefficient of 2xb is even simpler, is just 1. So what you get is this expression for S classical. M omega by twice sine omega TB minus TA times this combination xa square plus xb square cos omega TB minus TA minus twice xaxb. Let me just point out that if you take the limit omega goes to 0, this simply becomes m by twice TB minus TA times xa minus xb whole square, which, if you remember, is the action for the classical free particle. That's exactly what the limit omega going to 0 is supposed to give you. So now we have filled in the last link of our calculation for the propagator for a simple harmonic oscillator. We had calculated the normalization factor a while ago, and the non-trivial part, exponential I by h cross S classical, is just this much. So as you can see, considering fluctuations about the classical part considerably simplifies the calculation. So collecting the normalizing factor and the e to the power I by h cross S classical together, we get the propagator for the harmonic oscillator. Root over m omega by 2 pi I h cross sine of omega TB minus TA times the exponent of I omega m omega by 2h cross xa square plus xb square cos omega TB minus TA minus 2 xaxb divided by sine of omega TB minus TA. Now, this expression has one obvious problem which must have been noticed by you. Whenever sine of omega TB minus TA vanishes, this particular expression for the propagator appears to blow up. Well, actually, if you go back to our calculation of the constants A and B from the initial and the final points, from the boundary conditions of this problem, you can see that the real trouble starts there. Notice that the problem uniquely gives us A and B except for the situation where sine of omega TB minus TA vanishes. The physical reason behind that is pretty easy to understand if you just think about the way in which a harmonic oscillator oscillates in the classical scenario. Sine of omega TB minus TA vanishing essentially means omega TB minus TA has to be a multiple of pi, and that actually tells you that you have exactly half a time period apart. And if you are half a time period apart, then XA and XB have to be related to each other by a particular relationship. Otherwise, there is no possible solution to this problem. In other words, the boundary value problem, even in classical mechanics, breaks down under such a situation. In a later lecture, we will see exactly how this is handled. For the time being, let us confine ourselves to within one half period. That is, assume that the gap TB minus TA is not so large that omega TB minus TA reaches the value pi. So, In this lecture, what we have done is we have written down the propagator for the harmonic oscillator by considering fluctuations above the classical path, which simplified the calculation quite a lot. But we are not done with the harmonic oscillator yet. There are many other useful techniques involving path integrals that we can learn simply using the harmonic oscillator as a model. For example, in the very next lecture, what we are going to do is talk about using Fourier coefficients for the expansion to figure out the propagator. We will also talk in later lectures of other kinds of path integral expansions. Instead of using the resolution of the identity in terms of position and momentum eigenstates, we can use other resolutions of the identity. In particular, one which will be very important for us is the one in which we will use the coherent states of the harmonic oscillator to build up what is called a coherent state path integral representation. One reason why that is very useful is that it goes over rather nicely to the case where we are dealing with quantum field theories. We will also talk a bit later about a rather esoteric kind of harmonic oscillator, the so-called fermionic harmonic oscillator, where we will meet Grassmann numbers and learn how to deal with quantization involving situations where you have anti-commuting operators. But all these will have to wait. Bye till the next lecture, and hopefully that will not be delayed as much as this one has been.